Welcome to Microlecture 3, where we'll talk about molecular geometry, which is basically the shape of molecules. I'll start you off here with a discussion of regions of electron density. These are any bonding regions, like a single, double, or triple bond, or a lone pair of electrons. So on the left-hand side, we have three images where the central atom is surrounded by three regions of electron density. The sulfur has a lone pair of electrons on it, and then two double bonds, each of which is one region of electron density. You'll see that when the central atom has three regions of electron density, that imparts a flat shape to the molecule. So SO2 is trigonal planar. One might look at SO2 and think that it is linear, but after you draw out the valid Lewis structure, you realize that there is a third region of electron density, and that's causing the trigonal nature. On the right-hand side, you have molecules with four regions of electron density. Like water, for example, it's got two bonding regions and two non-bonding regions with its lone pairs. Arsine is a flammable, colorless, toxic gas. It's made when arsenic comes into contact with an acid. In any case, what you're seeing here is the molecular structure of arsine in 3 dimensions, and we're seeing that this lone pair actually crunches down the bond angle to a mere 92 degrees from what would be a normal tetrahedron. The textbook bond angle for a tetrahedral structure would be 109.5 degrees. Okay, so let's do example number 1 of talking about molecular geometries with acetic acid, CH3COOH. And if it is at all difficult to draw a valid Lewis structure here, then I do recommend that you go back and try to find some more practice problems going from formula to valid Lewis structure. So there are 3 hydrogens attached to the first carbon. The second carbon atom is attached to an oxygen via double bond, and then another oxygen via single bond. To complete the octets on the oxygens, they each have a couple of lone pairs, and there we have it, the structure of acetic acid. So let's talk about each atom in turn, each central or core atom in the structure. So carbon is central here at this location, and we could clearly count 1, 2, 3, 4 regions of electron density about that carbon. And so when atomic centers have 4 regions of electron density, they are tetrahedral, and they have a characteristic bond angle about the core atom. So we're talking about the bond angle from hydrogen to carbon to hydrogen, for example. Or we could really choose any of these bond angles. So we could likewise be talking about the bond angle from hydrogen to carbon to carbon. They're all going to be the same in this case because these are all covalent bonds around the same tetrahedral center, and so that bond angle right there, as well as this bond angle right here, is a characteristic 109.5 degrees. So that is the textbook bond angle for a tetrahedral center. Let's take a look at the next carbon atom over. So this one here, we have 3 regions of electron density about that carbon atom. We've got a single bond, and we've got a double bond, and then we've got another single bond. So that's 3 regions. That's how we would count that. And anything that has 3 regions of electron density is trigonal planar. And so this trigonal planar center has a characteristic bond angle as well. It doesn't matter whether we're talking about the carbon to carbon to oxygen, meaning this carbon to carbon to oxygen bond angle, that one, or if we're talking about oxygen to oxygen, so maybe we're talking about the bond angle right here. Any of the bond angles about that central carbon atom, okay, are going to be 120 degrees. And that's the textbook value for a bond angle about a trigonal planar center. The next atom that could be considered a core atom, so not on the periphery of the molecule, is this oxygen right here. It has 4 regions of electron density, so it is a tetrahedral center, and it should exhibit bond angles close to about 109.5 degrees, but we know that lone pairs will decrease the angle. Putting all this together then, when we draw acetic acid, we typically want to show the 3-dimensionality of the atoms. So for tetrahedral structures, we often draw 2 of the bonds on lines, one on a wedge, which means it's coming out of the plane, and one on a dash, which means it's going into the plane. And so there's our hydrogens, and we've got the other carbon. This carbon has 3 regions of electron density and is trigonal planar, so when we're trying to show its shape, we would orient these 3 bonding regions like so, as far away from one another as possible. And then the OH bond is there, but oxygen is shown with its lone pairs, and the bonds are bent around oxygen because of, again, the tetrahedral nature for regions of electron density. I just go ahead and complete the structure by drawing in any lone pair of electrons. Okay, so for example 2, let's do the same thing, but with acetonitrile, CH3CN. So this carbon is a tetrahedral carbon attached to 3 hydrogens, and we have another carbon, and it's a linear carbon attached to 2 things, so 2 regions of electron density. So a little bit more unusual. And then the nitrogen, of course, has a lone pair on it. So if we want to discuss the geometry about the atoms here, this one is a tetrahedral, and this one is linear. Bond angle for linear is 180 degrees. And that's it. We would expect the tetrahedral to have bond angles of 109.5. So for this example, go ahead and draw the structure of acetic acid, and then think about each of these bond angles and what they would be. Okay, so acetic acid. And first, we want to know the HCH bond angle. So if you follow the connectivity from hydrogen to hydrogen, it doesn't matter whether you choose that route or you choose that route. as long as you've found a hydrogen to carbon to hydrogen connectivity, then you'll get the correct answer. They are all 109.5 degrees if they're following a perfect tetrahedron. And then the next one is a carbon to oxygen. And so carbon to oxygen would be right there. There's no other connectivity of carbon to oxygen, so you don't have to worry about getting the wrong location in this molecule. And so there we have the trigonal planar. We said that bond angle was 120 degrees. And the carbon to oxygen to hydrogen, then the last one left here is carbon to oxygen to hydrogen, so it's that bond angle right there. And that one is tetrahedral as well. It looks a little bit like the bent bonds in water though, so we could assume that the lone pairs are crunching down the bond angle a little bit so that it will be a little bit less than 109.5 degrees. On a test or an exam you could say that, or you could predict a bond angle that is a little bit smaller, like 104 degrees. Okay, so for this example, we're just going to decide whether these two compounds are polar or not. That is, do they have a molecular dipole or not? Okay, so I've drawn out the structure of CF4. The goal here is to determine if there is a molecular dipole for this molecule. So is it polar or not? Remember that we have a way of notating whether a bond is polar or not, so we can use these crosshair and arrows to show the bond polarity and show that fluorine atoms are pulling on electron density. That's the more electronegative atom. But we see here that all fluorine atoms are pulling equally and oppositely. So from the carbon atom, which is in the center. So this is not considered a molecular dipole. There's no molecular dipole here, and this is therefore not considered to be a polar molecule. Likewise, we can draw the structure for NF3. We see here that, again, we have fluorine atoms pulling outward toward the periphery, but in this case, we've got a lone pair on the central atom, which means that the fluorine atoms are pulling in a net direction, which, as drawn this way, would be net downward. So there's a net downward pull of electron density here. And so, yes, there is a molecular dipole here, and NF3 is therefore considered a polar molecule.